Hi, my name is Matt Holliday and welcome back to my class on Programming in Go. In this section, I want to introduce traditional or conventional synchronization primitives. Now, that's not a put down. By primitive, I mean these things are basic or fundamental. In fact, the Go runtime needs them in order to implement select and channels. By conventional or traditional, what I'm saying is these things have been around forever. They're the only things available in many languages and systems. We could do all our concurrent programming with them, but I would prefer not to. I think Go's high-level CSP model is better, but these tools are in our toolbox and they do have uses, and this is the time to talk about them. In this section, I'm going to talk about primarily things that are in package sync and a subpackage called syncatomic. And what's in there are things like the mutex and the wait group. I've already talked about the wait group. I'm going to talk about a few of these other things. But before I do that, I want to talk about why. The problem we're trying to solve is called mutual exclusion. Now, the fundamental problem in concurrent programming is a race condition. And how do we solve a race condition? Well, we can try to make things that are read-only, and there's some other things we can do. But in the end, we may have things that we simply need to protect in a basic way. Okay, there's some piece of data that needs to be read and written to in multiple Go routines, or perhaps it's simply that's the best way to do it. Okay, and mutual exclusion is about preventing the race condition, because what it says is, well, either I'm looking at it or you're looking at it, or maybe one other thing is looking at it, but we can't all be looking at it and modifying it at the same time. Okay, and what that gets into is this notion of a critical section, which is simply a piece of code where we deal with that variable that needs to be protected. Okay, so when we're in the critical section, we need to exclude anybody else. And the most basic way to do that is with some sort of lock. Okay, I acquire the lock, I do this thing in the critical section, I give the lock up. And while I'm in the critical section, anybody else that wants to look at that variable has to wait until I release the lock. So I'm going to jump into the playground for a second because I want to start with the problem. And I've got a piece of code here. It's not terribly complicated. We've seen these things before, okay? So I'm really going to focus on this function do, right? Do is going to start a whole lot of Go routines, 1,000 of them. Now, all they're going to do is try to increment a variable that they can all see and modify, right? And I'm going to have a wait group because I need to make sure that we actually get all 1,000 of them to run and do their thing. Now, in theory, the goal here is I should print in the main program the number 1,000. Okay, so let's run this and see if that happens. Well, I get 988, I get 908, I get 940. I'm getting low numbers today because usually I get 970 to 1,000. And it's possible, by random chance, I might actually get 1,000, but it's unlikely, okay? Because I've got this data race right here. Okay, the formatting kind of moved my comment out of the way, but right here, this increment is a read, modify, write of a variable that's shared between the Go routines. Okay, it's a race condition or a data race. And what we know is, based on the examples we looked at a long time ago, that sometimes we're going to get two Go routines that get the value of n, they both increment it, they both store it, and one of those increments just disappears. And that's why the number, it's never going to be more than 1,000, I'm sorry. It's never going to be more than 1,000, but it's probably going to be less than 1,000, okay? If I did this with 10 Go routines, I might get 10 a lot more often. I did it with 1,000 to prove the point. It's fast enough, and we're almost never going to get 1,000 by accident. So we want to solve this problem, and we've already seen one tool to do that, right? In the last segment, when I talked about, actually the last two segments, I've talked about counting semaphores. And we saw the counting semaphore used in the file walk example to say, hey, I need to limit the number of Go routines that are active. Okay? Well, what I need to do here is limit the number of Go routines that are active in one part of the code, but I need to limit it to one. So one approach I could take, and we're going to try this, is I could actually, all right, make, and we'll just make it a channel of bool, all right? I'm going to make a counting semaphore, okay? But I'm going to make it a counting semaphore of 1, right? And if I do that, right, so what do I have to do? Well, before I try to increment my number, I have to try to push onto that channel. If I can, nobody else is using it. And of course, when I'm done, I need to read from it. So let's try that and see if that works. All right, I'll hit Format. Okay, so again, I've got my do. I've added this channel. The channel is a counting semaphore, but now it only has a capacity of 1. So let's run that. I don't know why I did that. All right, we get 1,000, and we get 1,000, and we get 1,000, and we get 1,000 again. All right, so this works, right? The same concept of the counting semaphore that limited the number of active go routines in our previous example, when we set it to 1, it limits the number of active go routines in this piece of code to 1 go routine. And now it's safe. This is a very useful tool, okay? Can we do it without channels? And the answer is yes, because the counting semaphore I'm modeling with a channel is behaving exactly the same as a lock or a mutex, okay? And in Go, it's actually called mutex. So I'm going to change this. Var_m is going to become a sync.mutex, all right? Instead of pushing to the channel, I'm going to call a function called lock. And when I'm done, I'm going to call another function called unlock. All right. So the mmutex replaces the mlimits channel, the counting semaphore channel. All right. And instead of reading and writing the channel, now I'm doing lock and unlock. Let's try that. And the answer is we get 1,000 every time. Okay, so the mutex is doing exactly the same thing as the counting semaphore with a count of 1. All right, except it's better designed for that. It's going to be a little bit more efficient, and it's more straightforward because now we have this, we're doing this very specific thing, all right, with a tool that's designed to do just this. So let me go back into the slides and talk about how we can use a mutex. All right, I showed it one way in the playground, and that way works perfectly well. It's actually better if we can embed the mutex into some other type, because that way we can make it part of the operations on that type. And in some sense, it's going to be a little bit safer. So here's an example where I've created something I call my safe map. Now remember, the original map in Go, it's not Go routine safe, all right? And we haven't actually demonstrated that yet. When we go back and look at homework 4 again, we're actually going to see that that's a problem. But here I'm just telling you this. So I have my map, which is inside this struct, and also I'm embedding the mutex. Now in this case, by embedding, that just means that the methods of the mutex, like lock and unlock, become part of my safe map. And that's a choice. I can do it that way. All right? So now I have my increment function, and my increment function takes a key and modifies the map, right? So some map entry becomes 1 more, and if it wasn't there, it becomes 1. And again, that's not a Go routine safe operation. I have to protect it, and this is one way to protect it, right? I put the lock in here, and this is also good style because I lock it and I immediately defer the unlock, all right? Because a very common problem with locks is, you know, you've got a function and you lock at the beginning, and then people start making the function a little bit more complicated. It starts having if-else, and maybe it ends up having more than one place to return, and suddenly somebody adds a branch that they forget to unlock in some particular case. And if you don't unlock the mutex, your program is probably going to grind to a halt. Okay, so again, this is a great use of defer. We defer the unlock immediately. There's no error to check, so we lock it, we immediately defer the unlock, and now we can do whatever we need to do, knowing that when we leave this function, we'll unlock the mutex so somebody else can use it. Great. So this is a basic use of a mutex. All right, it has a certain performance overhead. Right? When we use a mutex, typically we're going to drop into the operating system, and there's 2 things here. First, it has the same effect on readers and writers. So it doesn't matter what I'm trying to do, right? If I'm trying to read it or write it, it has the same cost. And sometimes that cost could cause my thread to get rescheduled. Now, there's a variant of this that's very, very useful in cases where we know that we're going to read way more often than we write. And that's the read-write mutex. Okay? And here's a little structure that has one. Now in this case, I didn't embed it. It's just a field, and I'll call it by name. So this is the other way you can do it. And it's kind of a design choice either way, right? So what I'm doing here is I've got some client that's got other methods. I'm only going to show a couple of them. I need a token. And most of the time, I just want to see, is my token still valid, meaning it hasn't timed out? I'll just use it. So the 99% chance is I'm going to call check token, get the token, and keep on going, right? All I'm going to do is read. I don't modify the object, I just read it. So in this case, I call a different set of functions, rlock and runlock. Okay? Now, what makes the read-write mutex different from the regular mutex is that it prefers readers, and it allows multiple readers to use it at the same time. Okay? When I lock for writing, all the readers have to be blocked. Okay? But when I lock for reading, other readers are okay. A writer will get blocked until I unlock, but multiple people can read and get the read lock, and that's very efficient, again, because 99% of the time, I'm just reading, and very quickly, right? Go in, get a couple of values, get out. Why do I need to protect them? Well, because every once in a while, the token will be invalid, and I'm going to call replace token, and replace token is going to do some logic and update the object. Okay? I need to change 3 things, and again, if I don't lock to do that, then this object is not Go routine safe. And I'm probably using it on lots of Go routines that are doing lots of queries to this microservice I'm talking to. Great. So, and there's another thing going on here, which is, I'm doing the expensive part where I just go off and get the token first. I don't need to lock to do that, right? So I do that part, and if that succeeds, now that I've got a new token, I lock the object, and in this case, I use the regular lock and unlock, because I'm a writer, not a reader. So I'm going to say, hey, lock it, no other writers and no other readers while I'm doing this. Okay, and then I update these variables. And again, I've deferred it, so when I return the new token and I unlock. Okay, so these are the 2 most basic things, a mutex and a read-write mutex, which is an optimization for the cases where I know that I'm going to have almost all readers and very few writers. And they're very powerful tools. Again, people have been building systems with these pretty much as long as we've been doing programming on modern computers going into the 50s. Okay, we could do it all this way, but it's difficult. We have to remember some rules about using mutexes that I haven't gotten into, and if we don't, we'll end up with problems on our program. Pretty much the main one being deadlock. All right, we'll make our program stop. Okay, now mutexes are in Go programs all the time because if you use channels, there's actually something like a mutex inside the channel. Okay, because channels need to be Go routine safe. All right, they're just smarter, and because they're not only smarter, but the stuff is embedded in the channel logic, we don't have to think about it. We just use a channel, and the right thing happens. Okay, and with mutexes, we've got to do a bit more thinking to avoid certain problems. Now, I want to bring up one other alternative, okay, and that's package sync atomic. There are some even more primitive tools which are more tied to the hardware that we can use. They're more limited, but sometimes they're more efficient. Okay, if I go back to my program in the playground, okay, right now I've got this mutex. Now, if I lock a mutex, I can do anything. I mean, I could lock a mutex and go off and do, under the lock, an HTTP query. I don't think that's a good design, but I could. Okay, but in this case, all I'm doing right here is incrementing a number. I'm doing a very simple addition. And the cost of getting the mutex is actually kind of high compared to the cost of just doing the addition. So it works, but there's something that's a little simpler or more primitive, if you will, that actually can work a little better. And what we're going to do is we're going to use the sync atomic package, and we're going to call a routine called atomic.addInt64. okay? And this is actually going to really depend on underlying hardware that allows us to do an atomic add. Okay, so we said the increment, right? The increment operation like n++ is a read, modify, write. That means we go to the hardware and we say, read this variable. Okay, now add one to it. Now write it. And that's not atomic in that sense. When we use the atomic add-int, we're actually saying, go and do an atomic increment at the hardware level. Okay, it's very efficient. And, you know, it works. I need to run that to get the package back. And if I run it again, I can run it several times. It's going to do exactly the same thing in a sense, but it did it a little differently. Instead of going and acquiring a mutex from the operating system, it just operates directly at a hardware level. So again, it's more primitive. Now, what can I do? Well, there's only 2 or 3 operations that are useful in the atomic package. Okay, primarily this one, which is an add. There's one that does a swap of 2 variables, and there's a third one that does something called compare and swap, which only does the swap if one of the variables has the value we think it should have already. Okay, and I'm not even going to get into that because that's a low level of programming that typically we just don't need unless we're doing runtime development. If we were building the Go runtime, we might use those things heavily. In a typical program, we don't. I just show this one case of the atomic add because that one's pretty valuable. If all we need to do is add a number, I need to increment a counter, then instead of getting a mutex, I can do this operation, and it's a little cheaper. So I'm going to go back to the slides and talk about 2 or 3 other things that are in the sync package, right? The first one is called once. Now, there's a pattern called the singleton pattern. Okay, actually I've named my thing here singleton, but there's a singleton pattern, right? The idea that there's one thing in the program that does this function. Well, that's great, but in a concurrent program, the question is not about having the singleton, it's about creating it. How do we make sure we only create it once in a concurrent program? Now, you might be tempted to come down here and say, well, in my handler, I'm going to look and see if x is nil or not, and then decide to make one. And I'm going to tell you right now, that's completely unsafe. It's going to be possible for 2 handlers to run at the same time and both try to create the singleton at the same time. Okay, so we can't do it that way. What we can do is use the sync.once type, which guarantees exactly once execution, right? So we do it, we have an object of type once, right? And we'll only be able to use it once, hence the name. And in the handler, we call it and we pass it a function. And the purpose of the function is actually to create the singleton and assign it. And by doing it this way, we guarantee that this function will be called exactly once. Well, okay, I suppose there's a chance if I never use this handler, it'll never get created. Okay, so maybe exactly once is not exactly the correct term, but it's never going to get created twice, right? It's going to get created once, hence the name. Okay, so this is another tool that's very useful. It has nothing to do with CSP. It is a mutual exclusion tool because it's a synchronization tool that says, yes, I'm going to make sure that if somebody calls once.do, nobody else is going to be able to call it at the same time. And once it's been called, anybody else who tries to call it will just return because they'll know under the covers that it's been called. There's one more thing in here I want to talk about called pool. Okay, now, in a long-running server, there may be things that we use a lot of. Connections, for example. And you're going to find out under the hood, if you look at things like gRPC or databases and so on, they're going to have connection pools so that connections can be reused because it costs a bit to set up the connection and to even allocate all the memory required. Okay, so you may decide that you need a pool of objects that you can reuse. All right, I go and get something from the pool, I use it, I put it back. It's more efficient sometimes than just allocating them all from scratch and letting them be garbage collected. Again, this is a problem of mutual exclusion because when I go to the pool and try to get something, I need to make sure that the logic that is involved in that is not being messed up by somebody else trying to do it at the same time. Because underneath there may be, for example, a queue of unused buffers. Well, we can't modify that queue concurrently safely. Okay, or we may find out that there are no extra buffers and one needs to be allocated, yada yada. Okay, so pool is a synchronous device, it allows us not just to manage the memory, but to manage it safely in a concurrent program. Now, it does have one limitation, and the limitation is that the things that we put in the pool itself just sees them as empty interfaces. All right? So we have to give the pool a function to create these things, whatever they are. Okay? In this case, it's a pool of bytes.buffer. Okay? So it's a bunch of byte buffers, and we can use them over and over again if we need lots of them and not have to allocate them from scratch. But when we go and get one from the pool, notice again, we're doing this thing called reflection. Again, I'm going to get to that very soon, so I don't want to go into detail now. But the pool is going to return us an empty interface, and we have to downcast that, if you will. We have to convert that from an empty interface to a specific concrete type. Now, in this case, notice that there's no OK, right? I can do there's operations where I can do it and get an OK value, the Boolean value that says, well, yes, it is of that type or not. In this case, if it's not really of that type, the program's going to crash with a panic. But I don't care because that's not going to happen. I created my pool specifically to have this type in it. So when the pool gives me a value, the only kind of value it can give me is the value I put into it, a bytes.buffer. Okay, so I'm just going to say in my program, yes, this thing is a bytes.buffer, treat it that way. All right, knowing that that's safe to do. Okay, there are other things in there, not a lot. There's a GoRoutine safe map. It has the same kind of property as the pool. It stores empty interfaces. So you can use that. All right, there's some costs about using empty interfaces. I won't get into that yet right now either. Okay, I don't know how heavily that's actually used. And of course, there's weight group. And we talked a lot about weight group already, which is why I haven't really talked about it in this section, right? I showed you using it in this section, and we used it in the previous section when we built all those file walk things, okay? And I'll bring it up again when we talk about gotchas. There's a gotcha, okay? We have to use it the right way. There's some other things in there, one of which is a condition variable. If you know what that is, great. If you don't, it's just not something I'm going to get into right now. I don't think it's necessary in Go. It's not very useful. I think the other tools we have in Go give us what we need, and condition variables, I haven't thought of a program where I could use a condition variable in a Go program. So that's my short introduction to the other concurrency tools that Go offers, besides channels, Go routines, and the select statement. Okay, these are older devices, if you will. They've been around in programming languages for a long, long time, and in some languages, that's all there is. They're still useful in Go. Again, the Go runtime itself depends on some of these, and the Go standard library depends on some of these, and you may find them useful in your program in particular cases. And in fact, when we do the next segment on revisiting homework 4, we're going to look at using one of these.